In this video, we're going to send a digital pulse train down an electrically long line. We have two mismatches which will cause reflections, the 100 ohm to 70.7 ohm transition, and we have a 70 ohm to 50 ohm transition. The reflections are going to interfere with our incident wave. We'll start out with the pristine digital signal, but as soon as we hit the reflection, we get ripples forming on the 100 ohm line. The reflection due to mismatch is interfering with the incident wave. The less pristine incident waves then get even more reflections interfering with them from the load, so we see even more ripples. So we end up with this digital signal that can have a lot of errors on it. If our voltage threshold for what a 1 or a 0 is around 0.4 volts in this example, we can see we get a lot of bits which would be read in wrong, causing bit errors. If the line was better matched and we didn't have the reflected waves, then we wouldn't have all of these ripples. This transmission line is electrically very long. It had to be long enough to show multiple pulses on the line. To put this in perspective, to show 5 pulses of a typical USB signal, the line would be around 1 kilometer long. This is a more realistic cable, around 10 meters long. With the shorter cable, we have less ripple. The voltage doesn't go up and down cleanly, but it doesn't bounce around as much either. But the signal is still bad enough that the line could have glitches. The line would have to be even shorter to eliminate the bounces entirely. This is why digital cables like USB, Ethernet, and the like are specified to have a maximum length they're allowed to be. USB cables, for example, are supposed to be kept under 5 meters.